Hey everybody, Mr. Slomka. We're going to talk about section 12.3 day 2. We did 12.3 day 1 yesterday, so we're going to continue on with 12.3 day 2. We're still talking about rates of change. We're still talking about the limit that is going to help us find the slope of a tangent line right there. Something that I didn't mention yesterday that I want to bring up today is another important term that isn't necessarily in the lesson here, but something that I want to bring up. I had mentioned that this right here is basically a derivative, which is very true. Another name for this is also called a difference quotient. Difference because it's got subtraction right here. Quotient because it's dividing. So if you ever hear me refer to a difference quotient, it's the same thing as a derivative, and it is this guy right here as well. Well, something that you should become very, very familiar with over the next couple of days because we're going to use it a lot. So today is a little bit harder examples. Let's see if we can try a couple of these out. So right off the bat, the directions are very much the same. Find the formula for the slope of the graph of f of x equal to the square root of x plus 3. Well, square root of x plus 3 is actually a curve. It's not a flat straight line graph. So to find the slope would be very difficult. So what we're going to do is we're going to create a tangent line, and then when we create that tangent line, then we can find the slope of that. Now they give us a point that they want us to find the slope at, and I will use that point. I promise I will, but not right away. What I'm going to do is I'm going to start with the difference quotient. I'm going to take the derivative, and then we can go back and use that point in a little bit. So here's what it's going to look like. My original part right here is I need to use the f function twice. The major characteristic of the f function is square roots, so I've got my square roots all set up. Now in my first square root right here, I need to put in not x plus 3, but rather x plus h plus 3 right there. So I'm going to have x plus h plus 3. There's your first square root. And the second one, see how it says f of x here and it says f of x here? They're the same. So that means you can use the exact same square root that you have right here, which is just going to be x plus 3. So to take care of this limit, what I would love to do is I'd like to go through my process. Direct substitution. Can I direct substitute? No, because I've got a denominator of h and it's going to turn into a 0. That's not going to work. So then how about simplifying and factoring? No, I can't do that because I don't have any powers. So then my next choice is rationalizing, and I have two square roots here, so I want to try to rationalize these guys. The way that you're going to rationalize is you're going to multiply by the conjugate on top and on bottom. The conjugate's going to look almost exactly like the numerator, except for the middle sign right here is going to change. So our first square root is going to be x plus h plus 3. Our second square root is going to be x plus 3. Both of these square roots are going to show up on top and on bottom, so we're going to have another square root with x plus h plus 3 and another square root with x plus 3. The only difference is that they are now going to have plus signs in between them instead of minus signs. Let's see what happens when we actually go through our work right here. So now you have to FOIL. When we FOIL these, you're going to get a lot of nice stuff in the numerator. So square root that's big times this other square root that is big, very much the same. So basically you just lose the square root. You keep your x, you keep your h, and you keep your 3. Then this big square root times the little square root that's positive, and this big square root times the little square root that is negative, those are going to cancel each other out, so you don't have to worry about them. And then the last two, little square root, you're going to lose the square root again, except it's going to be negative. So we're going to keep our negative, and we're going to keep our x plus 3, but we will not have our square root. Then down in the denominator, it's going to be a little weird. You got some square roots over here, you got an h that's not under the square root. It's so weird that I don't really feel like dealing with it, so I'm going to leave it alone. I'm not going to change it in any way. I can always go back and I can FOIL or distributive property later if I want, but maybe I don't need to. Hint, hint. That looks pretty good. So I have another opportunity right here to do some more simplifying. I can take my negative sign and distribute it to both of those terms right there. This is very, very important. You need to make sure that those parentheses show up so that the 3 becomes negative just like the x is about to become negative. So when this happens, this is going to allow us to do something very important in our next step. So let's take a look. Still starting all our problems with the limit as h approaches 0. That's just going to be kind of second nature to you in a little bit. You're just going to keep on writing it over and over and over again till you just kind of write it in your sleep, which is, in my opinion, a good thing. So we have our terms right there with our negatives, and we're going to keep that very big, very ugly denominator because it has not changed at all. So it's got the two square roots, lots of stuff. Alright, so here's the big important thing. This is why it's very important that the negatives end up in the right spot. We now have a positive h and a negative h. or sorry, positive x and a negative x. We have a positive 3 and a negative 3, and we are left with just one little baby h right up there. So that is really, really exciting. Our numerator just got a lot smaller. So now I'm going to rewrite my problem again. In my numerator, I now just have h, which is great. And then in my denominator, it's still the same big, ugly denominator that I've had all the way along, because I haven't really done anything with it, and I don't plan to do anything with it until I absolutely positively have to. So it looks like this. Now, if you look closely, you can see that you have h's on top and on bottom, and I'm glad that I didn't FOIL it or distributive property earlier, because now I can cancel them out. Hooray! So they're gone. That's so great. Let's take a look at what we got now. So now our limit looks even nicer still. When you're writing down this next step, please remember that something needs to go in the numerator. You removed all the terms, so the only thing you can do is kind of put a placeholder of 1 in there, and then we can keep our denominator pieces that we still have, like our x plus h plus 3, and our other square root, which is square root of x plus 3. Okay, so now I've officially unrationalized this problem. The square roots are down in the denominator, and I believe I've created a situation where I actually could direct substitute. If I take the 0 and I plug it in for h, I think it'll work. When you do this direct substitution, make sure you refrain from too much direct substitution. There are other variables like these x's, and I don't want you to replace them with a 0. They actually need to be part of our final answer, so don't get rid of them. So I'm going to keep those x's as x's. We'll lose the h, it'll become a 0, but the x's stay. So what's that going to look like? This is going to be the very first step I'm going to write down where I don't actually need to write limit, so I'm pretty excited about that. I can write it as 1 over the square root of x plus 0 plus 3 and the square root of x plus 3. Now if you look at those two guys right there, you'll notice that they're basically the same. The 0 isn't really doing anything for our problem, so you're basically talking about the square root of x plus 3 and another square root of x plus 3 right here. That means that I have 2 square roots of x plus 3. My final simplified direct substituted limit equation is going to be 1 over 2 times the square root of x plus 3. That looks pretty good. Okay, so now here's the thing. Some people are going to say, hey, don't we need to rationalize that final answer? And that would be a really, really great idea. And if you want to rationalize it, you can, which is totally fine. But also, if you don't want to rationalize it, I'll let that slide. Okay, so that's okay. The reason why I'm going to let this slide is because this isn't quite my final answer. I'm not putting a circle around this. This isn't the end of the problem. The end of the problem is actually the slope at the point 22.5. So this is an equation that will help me find that slope, but it isn't the slope itself. So I still need to do some more work. So if it was the very final answer and I wanted it to look as pretty as possible for my test or my quiz, then I would want to rationalize it. But this is not it. We still have a couple more parts that we need to get to, so let's see if we can do that. Like I have right here, I've got part B, and I've also got part C, so let's see if we can work on those parts. So this is good, and I like it, and I'm going to use it, I promise, but I'm not going to rationalize it because I really don't need to just yet. Okay, so let's do our next part. Part B says, find the slope of f of x at 22.5. So now what we have is we've got this equation that will tell us slope at any x value we want. We just plug in the x value right here and it'll tell us the slope. And so what we're going to do is we're going to take this information right here and our new equation and put them both together. So one of the things a lot of people ask is they say, hey, what about the y value? Do I need to use the y value? No, the y value is not very valuable. Only one we really need is the x value. So that means I'm going to put the 22 down here where it belongs, right there, and then I'm also going to have the plus 3 there because that is part of my final answer as well. And now I need to simplify this. Now this is a really great problem, and I set it up with really nice numbers so that the square root will work out really great. 22 plus 23 is going to give you 25. Square root of 25 is just 5. So we're talking about 1 over 2 times 5. Or more specifically, that's going to be 1 over 10. That's the guy right there. There's the slope that we're after. Cool. I like it. That is the slope of our tangent line. If you take a look at the drawing that I made up here, it was a very kind of shallow, not very steep tangent line, and it was definitely positive. Well, this guy fits the bill. It's positive, and it is very, very shallow. So if we are one of those people who was like, hey, that's a square root, it should be plus or minus, you're technically right, but for a square root graph, you only really need to worry about the plus part because there's only 1/2 of the parabola. There is no bottom U shape right down here, so you don't have to worry about the plus or minus. that is kind of convenient for you. Now the other part that you have right down here is part C, and part C is kind of like the extra add-on for the day, and what it says is that they want you to write the equation of the tangent line that passes through that point. So now I don't want to just know the slope of this tangent line, I want to know the whole equation. And so most of the time when you're looking for a whole equation like that, what I want is the equation to be in slope-intercept form. Y is equal to mx plus b. So we're going to use this point right here that we've had for a while, and we're going to use our new slope that we have right here, and we're going to put those two things together to write an equation in y is equal to mx plus b slope-intercept form. Now if you'd like, you can use this form right here to find everything you want, and it works out really nicely, and I bet you're awesome at that. So I will let you continue to be awesome at that if you would like. But I also have shown you the value of point slope form in the past, and I would like to try and kind of advocate for point slope form again. So what I'm going to do is I'm actually going to start with this form, and then I'm going to turn it into this form. And you don't have to do it this way. If you don't want to, that's totally fine, but I like to, so I'm going to show you what it looks like. So here's what's going to happen. I'm going to take my point, my 22 and my 5, and I'm going to plug it in for y1 and x1, and I'm going to take the 1 over 10, and I'm going to plug that in for m, and then I'm going to get my equation to look just pretty. So let's see what we can do. Y is, instead of y minus y1, I'm going to use my y value right here, so it's going to be y minus 5, and my m value is once again 1 over 10. X value stays the same, and then we're going to have our x1, which is going to be the 22. There you go. Okay, so now I just want to try and make this look pretty. I want to try and make it look like it's in slope-intercept form. So I'm going to leave my y terms how they are, y minus 5. I'll distribute my 1 over 10, 1 over 10x, and then right over here it's going to be negative 22 over 10. That's looking better. I'm going to reduce this 22 over 10 to make it look even nicer still. So that is going to be y minus 5 again. And then we'll have our 1 over 10x. And then 22 over 10 can reduce, and that's going to reduce down, has a common factor of 2, so that's 11 over 5. Then lastly, I'm going to bring my 5 over to the other side by adding it. Add 5 over here and add 5 over here. And that is going to give me my final equation, which is going to be y is equal to 1 over 10x plus 14 over 5. There is your final equation right there. That is the equation of the tangent line. Pretty cool. So this is something that we did yesterday, except for the square roots. We did that actually on Monday. So we're combining two things there. Then this is also something that we did yesterday at the very end of the lesson. So we're doing it again right here. And then now we're adding on this piece. And actually this piece is kind of arguably way back from algebra when you were in middle school. And I'm just bringing it back with this whole tangent line concept. Now, it's a lot of steps right there, so if you want to check your work, a really, really wise way to do that is to use your graphing calculator and just graph the actual original curve and also the tangent line. So if you take a look right here, if I go to y is equal to, you'll see that there's my original curve, square root of x plus 3. Then right here, you'll see that I have the tangent line, 1 over 10x, and then I've also got my 14 over 5 right here. I'm going to set my window, kind of a goofy window. I'm going to start at -5 and go up to 60. I'm going to count by 5s, and my y minimum is -1, and I'm going all the way up to 12. I'm kind of working my window right around the idea of this 22, 5. So I'm working with the 22 for my x's and the 5 for the y's. Let's take a look at what the graph looks like. It looks pretty good to me. So if you see, here is our square root graph right here, the curved one, and then right just glancing off the top of it is a nice tangent line, and they look great. They look really, really nicely and together, so I'm pretty convinced. So that is a really nice way to check. Definitely only crosses the graph once, probably right in there, and then it doesn't go back to it again. So that worked out really nicely. Thank you, graphing calculator, for helping me check. Okay, let's do some vocab. So now I've talked about it a bunch of times, and we're going to talk about it again. The word is derivative. In part A of the last example, we found a formula that can be used to find the slope of f of x at any point along its curve. So it's this tangent line slope thing. Mathematicians have always found these types of slope formulas to be very helpful and popular, so they gave them a special name. They call them a derivative. Asking for a derivative and asking for a slope formula for a tangent line are the exact same thing. You are finding them using the exact same technique. That technique is this guy right here. The fancy new name that I was talking about for that is that it's called the difference quotient. And so that is going to be your guy right there. One of the notations that we're going to use for derivatives is going to be not f of x anymore, but rather f with a little apostrophe after it. And that is going to be equal to this difference quotient. It's going to be equal to the derivative. The way that you read that is the exact same you used to read it back when you were in geometry class, and that a little apostrophe is called prime. So f prime of x. That is a way of distinguishing a derivative. So another one, there's a couple other ones, but there's one that's you got dy over dx. That's another cool one right there. D is kind of her derivative. We're going to try and talk about that one in a little bit, but this one's a pretty elementary one, so this is a good place to start from. So a couple of words, we've got tangent line, slope, we've got derivative, we've got difference quotient, and we've got prime now, and they're all kind of talking about the same thing. They're all in the same soup of calculus right here. All right, on the back side is a little bit more of the same. We're just going to up the ante, make it a little bit more complex. So I've got in my next problem right here, this one just says find the derivative of the function. So there's our new word, derivative. We are officially doing it now, and we're going to officially do it in the exact same way that we've been doing it for the last couple days. So it's not new or exciting, but the directions are slightly different. So my equation this time is actually a fraction, which is also something we've done in the past, but I've had questions in class about it, so I'm pretty sure that it's something that a couple of you are shaky on, so let's go over it. If we're going to work with this fraction guy right here, we're going to do it in the same kind of way. We need f of x plus h minus f of x. So for f of x plus h, that means that down here in the denominator, it's not just going to be x and 5, it needs to be x plus h plus 5. So there's your first denominator. Then for the second one, see how that guy says f of x and this one says f of x? They're the same. So what you can do is you can copy the exact fraction down exactly how you saw it before. X plus 5. We'll still have our denominator of h down here. Now when you have fractions like this, you are not going to direct substitute because you'll end up with a denominator of 0. You're not going to factor. You're not going to unrationalize. You're going to have to do something different. And the different thing that we have for these kinds of problems is common denominators. We've got two fractions right here and they need common denominators. Let's see if we can create them. So for my first fraction, what I really need to multiply by is everything that I see down here. I need to multiply by x plus 5 on top and on bottom. For my second fraction over here, I'm going to need to multiply by something bigger, x plus h plus 5. So we'll multiply by x plus h plus 5 on top and another x plus h plus 5 on bottom. So it's going to be double trouble. Okay, let's take a look. So for my first fraction, I'm going to multiply, and I'll have my x plus 5 in the numerator, and my denominator is going to be huge. It's going to be x plus 5 and x plus h plus 5. Once again, I could FOIL this all out, and that would be really cool, but you don't really need to just yet, so I'm going to hold off. I'm going to be lazy, and maybe that laziness will pay off. It's paid off in the past, and maybe it won't. And if it doesn't, I can always just FOIL it later. But maybes. So I'll hold on to my maybes. I'll hold on to my hope. Okay, we now have common denominators. They're big and they're ugly, but they are common. So now we can do our subtraction. When you're doing your subtraction, remember you are subtracting every single term that you have up here. They are all being subtracted. So you need to make sure you note that when you're doing your next step right here. So we'll still have our limit as h approaches 0, and we'll have our x plus 5 in the numerator, and now we're going to be subtracting an x. We'll subtract an h, and we're subtracting a 5. Those are all the things that are in the numerator now with subtraction on them. We still have our common denominator that is big. It's got the x plus 5 and the x plus h plus 5. And we have our very, very big denominator that's always kind of there lurking around until the last couple steps, h. Okay, so now here's our next cool step. The reason why you need to make sure your subtraction works so well is so that your canceling works out really well here. X's are going to cancel. 5's are going to cancel, and you're left with only a single term here in the numerator, which is great. So let's take a look at what the equation looks like now that we've kind of trimmed it down. We have our negative h, and we've got our beast of a common denominator, x plus 5 and x plus h plus 5. And the whole thing is over h. Now this is called a complex rational. You have fractions inside of a bigger fraction. And when you have these kinds of things, dividing by this denominator right down here is not as helpful as multiplying by its reciprocal. So my suggestion would be to use the numerator exactly how it's been showing up the last couple times, not changing it at all. But instead of dividing by h, I would multiply by its reciprocal. So that h right there is actually h over 1. I'm going to multiply by 1 over h. This works out really nicely because now you have some h's that can cancel out as well. Be careful when you're doing this canceling. You are not losing the negative sign. It stays. And you're also not losing the 1. It stays as well. So those things are going to stay in the numerator. This is what's going to be left in the denominator. A couple steps more and then we'll be all set with our derivative here. Woohoo! So in the numerator we have our negative 1, which is great, and then in the denominator we still have our x plus 5, x plus h plus 5. Are you getting tired of writing that? Me too. I think it's time for direct substitution. So we've limited it down to only a single variable h, which is great. I'm going to direct substitute into that guy and see what I end up with. I do not need to write limit as h approaches 0 out in front anymore. I am free of that because I am now direct substituting, so I can just write down my fraction with my 0 in it. When I put that 0 in it, it's really not going to do anything, so I have an x plus 5. I have another x plus 5. The simplest way to write this derivative is to write it as negative 1 over x plus 5 squared. Okay, so now how about some notation? This guy right here is technically our derivative, so what you could do is you can write m is equal to that guy, because it's going to help you find the slope of a tangent line, but you can also write f prime of x is equal to negative 1 over x plus 5 squared. That's also fair game. So I like this one. This one's kind of new and exciting. This one's also cool because it's a throwback to what we did yesterday. Both of them are legitimate. Both of them are good. When you see the word derivative, I'm going to kind of hope that you kind of sway more towards this way. And if the word up here had been slope, then I would like you to try and sway towards this way. But they're both good. As long as you have this part right over here, that's the main thing that we're after. But these two guys are also fun to talk about, so that's what we're doing. All right, so now that's the real calculus part, but to kind of increase the complexity of the problem, make it a little bit more honorsy, what we have right here is we're asking another question that really is rooted in algebra class back when you were in middle school, and it's going to ask you to deal with and work with this derivative in a couple different ways. So it really kind of shows, can you take a derivative and do you know what it represents? So right here it says, use your derivative to find the equation of the line that is tangent to f of x equal to 1 plus x plus 5, which is the exact same equation we had right up here, and parallel to y is equal to negative x plus 13. So I'm asking you to make a line that is parallel to this guy and tangent to this guy. It's kind of this double-edged sword that we're dealing with here. So let's deal with one part at a time. First of all, parallel. Parallel is an old term. We've seen it in algebra class, and it really means something. It means that they're going to have the exact same slope. So if you can tell me what the slope of this equation is right here, then you can tell me what the slope of our tangent line is going to be. Well, the slope of this equation right here is stuck right between the negative sign and the x. It is going to be a slope of negative 1. That's the slope that we're really after right there. So then the question becomes, well, what x values would you have to use to get that slope of negative 1? So now I'm going to use my tangent equation right here. And usually I plug in x values to my tangent equation, but this time what I'm going to do is I'm going to plug in a slope, because I now know what the slope is. The slope is negative 1. So it's going to go into the tangent equation as opposed to the x values like I usually use, like I used on the front side. So I'm going to have my negative 1 out in front, then I'll have my equal sign, and I'll have another negative 1 over x plus 5 squared. Whoa, look at that guy. Cool equation, easy to solve, lots of different ways to solve it. So I'm going to show you one way, but there are others. So if you don't like the way that I solve it, go with your gut. Use your own technique, because I bet it's good, because you're good at your algebra. I know that we're all very, very good at our algebra, so I'm not concerned about that. I find that most kids like cross multiplication, so that's the technique that I like to kind of convey because more people are comfortable with it. So I'm going to cross multiply, and that's going to give me negative 1 times x plus 5 squared, and it'll also be equal to negative 1. No more fractions, which is great. Then I can start kind of whittling away to get my x variable by itself. I'm going to divide by negative 1 on both sides, which is going to give me x plus 5 squared equals positive 1. And then what you could do is you could start foiling this if you want, but something else that works out pretty nicely is you can use a square root. So once again, I'm only showing you one way to do this. There are many other ways to do it, so if you don't like my way, that's okay. If you use a square root, which is a really great technique, you have to remember what the square root of 1 is, and it might be a little surprising for some of you. The square root over here cancels out, and we're left with just x plus 5, and on the other side, where the 1 used to be with this new square root, the square root of 1 is actually plus or minus 1, which means that we now have to take this equation right here and we're going to split it up. That means that x plus 5 is equal to 1, and it also means that x plus 5 is equal to negative 1 because of the plus or minus right here. I'm going to get two different x values. The two different x values that I am going to get mean that I'm also going to probably end up with two different equations that they're after right here. So they're after equations, but we're going to end up with two of them. So one of my x values that I'm going to get I'm going to move my 5 over to the other side for this one. Minus 5 means I'm going to have a 1 minus 5, which is going to be negative 4. The other one is going to come from this guy right here. I'm going to move my 5 over. Negative 1 minus 5 means I'm going to also get x is equal to negative 6. I have two x values right here. Next thing, for our next piece, having an x value by itself is not really helpful. It'd be great to have some y values to go with them. So it says what are the y values that are attached to those x values, and so we're going to find those as well. To get those y values, we're not going to use the slope equation. What we're going to do is we're actually going to go back to the original equation that we have right here and find the y values. So our original equation is 1 over x plus 5. That means y is equal to 1 over x plus 5. Let's take both of these x values and plug them in so we can get some y values to go with them. So that means we're going to do 1 over negative 4 plus 5, and we're also going to do 1 over negative 6 plus 5 to get some y values. First y value I'm going to get is right over here. Negative 4 plus 5 is going to be 1. 1 over 1 is going to give me a y value of 1. This guy right here, negative 6 plus 5 is going to be negative 1. 1 over negative 1 is going to give me a y value of negative 1. So that gives me ordered pairs. So now I have x values right here, and I have y values right here. So let's talk about the ordered pairs that we have. I now have an ordered pair that has a negative 4 and a positive 1. And I have another ordered pair that starts off with a negative 6 and a negative 1. These are 2 points that are on the parabola, a hyperbola, I should say, and these are 2 points that are going to have tangent lines that are parallel to this guy right here. But we're still not done. To continue on with this problem, to really just drag it all the way out, we actually need to write slope-intercept equations for both of the lines. The lines are going to pass through these points. They're going to be parallel to this guy. They're going to be tangent lines, all of the stuff all in the same time. Luckily, we don't have to use all the stuff at the same time. We're basically whittling it down. We're getting very, very close. The main things that we need to remember is that our slope is going to be negative 1, and we're going to have a point like negative 4, positive 1. And then we're going to do the whole thing all over again, and we'll maintain the exact same slope of negative 1, and we're just going to do it with the other point, which is negative 6, negative 1. Now, last time when I did one of these, I used point slope form, and I felt like it worked really well, but I also know that some people don't really like it. So if you take a look at this one, I've set it up so that we can find our b value using a slope intercept form. So I'm going to go back and I'm going to use the y is equal to mx plus b technique that more people seem to like. So you have choices. You have choices in a lot of these different things that end the problems, so you can use them however you'd like. So if I set it up y is equal to mx plus b style, that means I'm going to use my y value of 1. It's going to be equal to my slope of negative 1 and my x value of negative 4, and it's going to be adding on the b at the end. I need to solve for that b right there. Negative 1 times 4 is going to be positive 4. I'll move that positive 4 over to the other side by subtracting it, and I'm going to end up with a y-intercept of negative 3. Negative 3 is equal to b. Then I'm going to do the same kind of thing over here with this guy. I'm going to start with my y value, which is negative 1, and my slope, which is negative 1. I'm going to use my x value, which is negative 6, and then I'm solving for b at the back. Negative 1 times negative 6 is positive 6. I'm going to move that positive 6 over to the other side by subtracting it, and I'm going to end up with negative 7 to be my b value right there. That means that my final equations are going to once again have the same slope, because they're going to be parallel, of negative 1, and my first is going to have a y-intercept at negative 3, and my second is going to have a y-intercept at negative 7. Whoa, that was a lot of work right there. It's so much work that it would be really, really nice to try and check that work in a nice quick way. And we know of a good quick way to check that work, so I'm going to try and do that. And that quick way is to once again reach for your graphing calculator. So what I'm going to do right here is I'm going to grab my graphing calculator. I'm going to go to y is equal to, and I'm going to start typing in a couple of these equations. So the first equation I'm going to type in is actually the original fraction equation, 1 over x plus 5. And then I'm going to type in my 2 tangent line equations that are supposed to be parallel and all that kind of great stuff. When I graph this one, you can usually just use a pretty standard zoom most of the time, and that works pretty nicely for here. There is your hyperbola from your fraction, and then there are your 2 parallel lines right there. They worked out really nice. Definitely are going to be tangents, and they are going to be parallel. So it looks really, really nice. Good check. Very quick to do. Last one, last example that I have for you right down here. If you're looking at your note sheet, it's all written out for you. So I will let you read over that, and then if you have any questions, we can go over it in class. The cool thing for this one is asking about a tangent line is horizontal. What that really means is that you are hunting for a slope of 0. That's what it means. So if you take a look right over here, we are finding our derivative, and then we take our derivative, we set it equal to 0, because that is what means horizontal. And then lastly, we solve, and shockingly, once again, we get 2 x values. So then we are going to get 2 sets of information right here. We'll end up with 2 different points. If you have questions about that problem, come talk to me in class, ask your friends, and we can get it all straightened out, I promise. I'll have more videos for you tomorrow. Good luck with your AP testing. I will see you soon.